Last week we started looking at sequence networks. We started out by talking about Fortescue's theorem. We looked at how to represent individual components or sections of the network. And we also delved a little into three-phase systems, just looking at zero sequence, currents, etc., etc. Today we want to try and put all of that together, along with what we did first couple of weeks, which was per unit. So I want to try and put everything that we have learned so far together. And the first area of application is in fault analysis. So if you recall, Fortescue looked at how we would represent and set a set of unbalanced phasors with the use of a set of balanced phasors. So where you have your phase currents being unbalanced due primarily to faulted conditions, then you will be able to represent each of those currents or calculate each of those currents by application of Fortescue's theorem. Now, you will do a lab that looks at fault analysis, and that will be a little bit of after the class. You will do that lab. So what we're going to be focusing on this afternoon is more or less the background activity to what you would have seen, or what you will see rather, on the or in the program. So the program is just doing the calculations, giving you the results. What we are going to be looking at is how we actually get the values, current and voltage values, etc., etc., etc. All right, so let's get started. Now we have a three-phase system, so it means that any one of these phases can be faulted. All right, so we can have either the phase A, B, or C on the fault. However, to introduce this topic, the standard is that we assume phase A to be involved with a ground fault. So phase A is touching ground, all right? And where there are phase faults involving more than one phase, or should I say two phases, the assumption is that it involves B and C. But we do that with the full understanding that it could have been A and B, A and C, etc. The bottom line is that the calculations will remain the same. It's just that in terms of the equations and the displacements that you'll be using are slightly different, but the principle remains exactly the same. All right? So we start out by looking at the first fault type, which is that you have a line coming in contact with the ground. Now that can happen, a myriad of ways. One, the line can come in contact with a tree. So, during heavy wind, or for some reason a limb of the tree is broken, but still attached to the tree. The tree touches one of the phases, and you would then have a phase to ground fault, right? Because the tree is in firm contact with ground. Other ways you can create ground faults, it's just by human error. Incidentally, this is the most common fault type that occurs. All right. So more often than that, when you have faults on the system, it's usually a single line. So we start out by talking about what you have on screen there, the boundary conditions. What do we mean by the boundary conditions? And simply put, the boundary conditions looks at those things that you know, the things that are true based on the type of fault that you have. So if I have a fault on phase A touching ground, what would be the voltage on phase A? Anybody? If phase A is touching ground, what would be the voltage of phase A?
0, sir.
0, right? Because it must be at the same potential as ground. So although you're dealing with this high voltage system, if that phase comes in contact with ground, then one of the boundary conditions is that the voltage is 0. All right. The other boundary condition, and in looking at this first section, I'm going to go a little slowly because we have to go through the same process for the others. But if we understand the basic principles here, then to make the others much easier. So for the boundary conditions, we're always looking for what is happening on the voltage side and on the current side. The other boundary condition has to do with the other two phases. Now, this is let's just say it's theoretically true. However, practically this is not the case because the fact that you have phase A in touch with ground does not necessarily mean that 0 current will be flowing through the other phases. All right? But theoretically, IA would be a maximum. All right? So we'd have a high current flowing through phase A. The voltage of phase A at the fault point would be 0. All right? But IB would be equal to IC and would be equal to 0. So what we usually say is that relative to the fault current that is passing through the faulted phase, which in this instance is phase A, relative to phase A, IB and IC are 0. All right? So having said that, we now go back to the equations that we had developed from Fortescue. So we know that IA is equal to I0 plus I1 plus I2. We have the equation there for IB and IC. And if you recall from last week's lesson, this is where we had gotten the T matrix. All right? Where you had the 1, 1, 1, 1 A squared A, and 1 AA squared. All right, remember that? So this is the equation that we had then. Okay. Are we finished with this? All right, now, based on the boundary conditions that we have here, we said that IB was equal to IC was equal to 0. So we can equate those two equations. So if we equate equations 2 and 3, all right? And of course, whether or not they were equal to 0, if they are equal, all right, they are equal. These two are equal, then what we are saying is that we are going to be equating these two equations. All right, so if I equate those two equations, I'm left with that. Of course, the I0 would disappear. And if I rearrange and factorize, I will get A squared minus A times I1 and A squared minus A times I2. Now, regardless of what this works out to be, we're not interested in that right now. But regardless of what it works out to be, what we know is that a squared minus a must be equal to a squared minus a. So they are equal. And by that token, it means that I1 is equal to I2.
1 equal I2.
All right. So what we are saying is that the two sequence currents, remember, and I want you to make the distinction. Remember what we have here in terms of the boundary conditions. These represent the phase currents. So it's a phase currents. What we are showing here are the sequence currents. All right? So the positive sequence and the negative sequence currents are equal. So based on this, if I select any of the three equations that we looked at earlier, right? And if we look at equation 2, and I'm going to now substitute or make the substitution in terms of I1 and I2, all right? Remember, if we look at equation 2, yes? Bearing in mind that we are substituting I1 equal I2. Right, so where we had a squared I1 plus AI2, so we now have a squared plus a I1. Would have been the same equation, which would have been a plus a squared I2, yeah? Of course, you can just make a note that 1 plus a squared is equal to 0. All right? So 1 plus a squared equals 0. Which means, therefore, that a plus a squared, all right, so a plus a squared is equal to minus 1. All right, you can test that when you have time, but just take my word for it. So a plus a squared is equal to minus 1. What that is saying, therefore, is that 0 is equal to I0 minus I1. So we now have a relationship, because if I1 is equal to I2 and I0 is equal to I1, what that is saying to us is that all three currents are equal. So I0 equal I1 is equal to I2. Another way of putting it is that IA, because remember the faulted phase was the A phase. So IA is equal to 3I1. Since all three series sequence currents are equal, so we'd have IA, go back to the original equation, IA was equal to I0 I1 plus I2. All right? So since they are all equal, then IA is equal to 3I1. Of course, that's equal to 3I0 equal to 3I2. But for our purposes, we usually just say it's equal to 3I1. And you will understand, or you will see why in a few minutes. Any questions? Any questions? All right. Now, remember, we said last week we were looking at representation of different pieces of equipment. And what we did, we showed that you had a positive sequence representation, you had a zero sequence, and you had a negative sequence representation for each piece of equipment. Good? Now, if it is that for the network, the zero sequence is equal to the positive sequence is equal to the negative sequence. The only condition for these three circuits to be in series, for them to have the currents being the same, what that is saying to us is that the sequence networks are connected in series. And remember, we are also stressed the direction of the current. So for your positive sequence, this would be a positive sequence network. Now it must have the generator, because the generator, in terms of the representation, if you recall, for the generator, you had that, okay? And of course, I1 flowing out. So for your network, you will have generation, right? Because your system is going to get the fault current from the generator, right? So this would be your equivalent positive sequence network. This would be the equivalent negative sequence, and this would be the equivalent zero sequence. So once we have those individual networks, what we are saying here by this analysis is that the positive, the negative, and the zero sequence currents are all equal, and therefore an indication that the networks are connected in series. All right? And if you note, it's important that we note the current flow. Right? Note the current flow. Right? So the direction here corresponds with I2. This at the bottom, it corresponds with I0. Yes. So when we talk about equal, and now we're in power systems, all the principles, all the networks principles now apply. If I say that they are equal, it means that they must be equal in both magnitude and direction. All right? Okay. Any questions? Is there anybody in the room? Oh, okay. All right, next. Pardon?
We're here, sir. You gotta teach, man. Do your thing, man. We're here.
I hear you. All right. So, as I said before, the other possibility is that you have two phases coming together. Are we looking at a line to line to ground? All right. So you now have two lines coming in contact with each other, but in addition, they are also in contact with ground. So we start out as before. We look at the boundary conditions. For this boundary condition, bearing in mind that it is phases B and C, which are now in contact with Earth. So once again, the cause or causes, possible causes for a line to ground would be similar for a double line to ground. Again, it could still have a tree. And instead of only touching one phase, it touches two phases. All right? So if I now have the boundary condition where B and C are in contact with the ground, what will be the condition? What will be the boundary condition? What are the boundary conditions? What do you know must be a fact?
So VB and VC equals 0.
Thank you. So VB is equal to VC, is equal to 0. And of course, as we showed before, the unfaulted phase relative to the two faulted phases would have a current of 0. So we say that IA is equal to 0. All right? Now, based on these boundary conditions, whereas for the line to ground, we considered the currents, for the line to ground or double line to ground, we're going to be looking at the voltages. So VA is equal to V0, V1, V2, and we have the expressions of VB and VC. Once again, we know about VB and VC based on our boundary conditions. So if those two are equal, which are equal to 0, yes, then we can equate these two. All right, so we can equate those two. If we do that, then we have similar expression to what we had earlier. The only difference is that now it's in terms of the voltages. All right? And we simplify in a similar manner. Again, doesn't matter what A squared minus A is equal to. Yes. What this implies is that V1 is equal to V2. Now, I mean, you know, we use whatever mathematical machinations facilitate an acceptable output. So we know that VC rather was equal to VB, which was equal to 0. So if I add 0 plus 0, I still get 0, no? So I play around and say, all right, B plus C equals 0. So I add those two equations. And we already established that this was equal to minus 1. So when I take that over, I get V1 plus V2. But again, V1 equals V2. Yes? So I get 2V0 is equal to 2V1, or V1 equals V0. Right? So we have V0 equal V1. We have that V1 is equal to V2. All right? So again, if the three networks all have the same terminal voltages, if you go back to the equipment representation, remember we had, for example, for the generator, we had that. We said that between here, this would have now been V1. That would have been I1. Yes. This would have been Z1. And of course, that would be a G. Yes, Miss Michael.
Good evening. Sir, could you
Afternoon. You're very low.
Could you return to the previous slide, please?
Okay. All right.
Yes, sir. Thanks.
So it means, therefore, that for all the networks to have the same terminal voltage, all right, if all the terminal voltages are equal, what that is saying to us,
So
that,
the terminal voltages are in parallel, sir?
that the networks are in parallel. Yeah. All right. So it's telling us that the networks are connected in parallel. Okay. All right. So now bear in mind, students, that there are other fault conditions such as open circuit that we can consider. If you are so interested, you can do those or create those faults when you do the fault lab. All right. Okay. So next, the next possibility is that the two lines somehow come in contact with each other. Yes, I need to also make the note that what we're looking at here, or these fault types, are what we refer to as unsymmetrical faults. All right, where not all phases are impacted in the same way. So your symmetrical fault would be a three-phase fault. So all three phases are impacted simultaneously. All right. So we are looking at unsymmetrical faults. Just a note. You will look at three-phase faults using your lab exercise. So here we have both lines coming in contact with each other. So what will be the boundary conditions? So B and C are now in contact. What do we know? What facts do we know?
Sure, B and VB is equal to VC.
Okay, so that's the first one. In terms of the voltages, B is equal to C. Good. Next, what else do we know?
Sure, ID is equal to IC.
Explain that a little. How you get that?
So I was saying that if both of them are in contact here, then the same current will be flowing through both of them at one point here.
Okay, so if a current is coming out of IB, where is it going?
to IC
right?
or through C, sir.
Through C, yeah. Now, we'll be going in the same direction as the current through B.
No, sir. So they're going negative.
Okay, so
You
give
see.
it the boundary condition.
IB is equal to I minus IC.
Absolutely. All right, because you can only have one current. Yes? And the current
Okay, sir.
coming out of B must be the current going into C because the two are now connected. You with me? That's where the fault occurs. So, good. So the boundary conditions are that IB is equal to minus IC and VB is equal to VC. So we first start by looking at the voltages. So again, we put back our three equations. What we know is that B and C are equal. So we can equate those two. And as before, we did this just now with a line to ground. Yes. As before, we know that V1 is going to be equal to V2. We have this?
No, sir. Yes, sir.
So that is it for the voltage. We now look at the current. So for the currents, we again write back our equations for the currents. And what we know from the boundary conditions is that IB is equal to minus IC. Okay, so we equate IB and minus IC. If we do that, ready again? If we do that, then we get twice 0 minus I1 plus I2 equal to 0. We rearrange that. Now, big question. What is I0 equal to for what we are looking at? We have two lines coming in contact with each other. What is I0 equal to? Everybody?
So is it 0?
You're asking me? Are you telling me? Hmm?
So I was asking, but I'm thinking about it now.
Come on, talk, man.
Sir, I would say 0, sir, probably because it's a short circuit.
All right, what does I0 represent? What is I0?
Zero sequence current.
Zero sequence current. Now, what did we say about zero sequence currents last week? Think about, yeah, what did we say about zero sequence current?
Sir, they cannot flow unless there is a path to ground.
No, you went low just now. Go again?
Cannot flow unless there is a path to ground.
Absolutely. Now, is there a path to ground here? No, because you only have the two phases coming together. There is no connection with Earth.
Okay.
Okay? So
Yes,
there will
sir.
be no zero sequence current. So 2I0 would be 0. So you get I1 is equal to minus I2. All right? So V1 is equal to V2, and I1 is equal to I2 minus I2. All right? So based on those relationships, where you have the terminal voltages of both networks being equal, and the current leaving one network is the current entering the other. What can you say about how the networks are connected?
Sir, could you repeat that, please?
If you have the two terminal voltages equal, which is what we just showed, I1 is equal to I2. Yeah? What did I just say? I1 equal I2? Yeah. I think I
There
had my
mean
lunch.
VB equal.
My lunch too late. V1 is equal to V2. That's what we showed earlier, right?
Yes, sir.
V1 equal V2. And I1 is equal to minus I2. If those are the conditions, what can we say about the two networks for those conditions to be true? You want the conditions again? V1 equal V2 and I1 equal minus I2.
Sir, is that a two-point network?
No man, how are the networks connected?
So series parallel.
You have two networks, the two voltages. Did I give you the oh yeah, I gave it all right. So they have two networks. The voltages are the same, and the current leaving one is the current entering the other. How are they connected? Huh?
Cascade then.
You see, I bet if it was another lecturer who didn't do networks, you wouldn't tell him that. They are simply connected in parallel. Remember, terminal voltage across here will be V1. The terminal voltage across here will be V2. I1 is equal to minus I2. Agreed? So the networks are connected in parallel. So let's try and concretize a few things. All right, I'm just gonna give you the steps that will be applied for fault analysis. All right, let us write the steps, and then we look at a problem or two, and try to get a good understanding of what we're dealing with today. All right. So here are the steps. Are we finished with the circuit? Okay. So fault analysis steps. Now, I know it's all on the screen, but I'm going to read them anyway and try to explain them one by one. The first thing we need to do is to redraw the original network, replacing each component by its symmetrical equivalent. Yes. To form its per unit, positive, negative, and zero sequence networks. So some keywords there. We're just gonna redraw the original network. So whatever network you get, you're gonna redraw it. And each component, so remember last week we looked at how you represent a line, how you represent transformers, how you represented loads, how you represented generators. You remember all of that? What we are saying here is that each component of the network must be represented by its symmetrical equivalent. Are we using here symmetrical components, eh? And we are going to form, ladies and gentlemen, you put up a per unit assignment. You're going to now form per unit positive, negative, and zero sequence networks. Step 2 is that you're going to derive, and this word comes up again. We all thought you had forgotten him. You're going to derive the Thevenin equivalent at the fault point for each network. It's quite simple. What we're saying, just like when you were looking at Thevenin equivalent, you were removing the load at a particular point and then looking into that pair of terminals for the Thevenin equivalent. That's exactly what you would have been doing here. And I'm choosing my words carefully. You would have been doing that. Step 3 is that you're going to be connecting the Thevenin circuit. So after you have found the Thevenin equivalent, all right, now bear in mind that the Thevenin equivalent would just be a source and an impedance. In power systems, the Thevenin equivalent would also be just an impedance. So you're going to have source and impedance, impedance only, and you're going to then connect them depending on the type of fault that you have. So what we just went through, if it's a single line to ground fault, you'd connect the 3 networks in series. If it's a line to ground fault, then you'll connect the networks in parallel. And of course, if it's a line-to-line fault, then you would connect the positive and the negative sequence networks in parallel. So one of the common things that's done, in this particular topic is that you're going to have more information than you really need. All right, so you're going to have more information than you need to solve the problem, but you must determine which information is of value. Step 4 is that you're going to calculate the per unit sequence currents at the fault point. So you're going to calculate the per unit sequence currents at the fault point. And this is the beauty of per unit, because the other section of this statement is that you calculate the currents at the fault point or other sections of the network. Now, when you're moving to other sections of the network, you're going to be going across transformers. But because the network is in per unit, it doesn't matter. So you won't have to consider the turns ratio of your transformers. All right? So having gotten the Thevenin equivalent, you then reverse it to get the current in the different parts of the network. All right? Because at the fault, of course, you're going to have contribution from different parts. Then you go to your newest friend, the one that you will save in your calculator. And it may be the only formula that you're allowed to program in your calculator. So program the matrix, because you're going to be using it over and over. All right? So you use the T matrix to calculate the corresponding per unit phase values. So here, what you have are the sequence currents, which is the I0, the I1, and the I2. You then use the T matrix, and you're going to find now I, A, B, and C, or V, B, A, B, and C. All right? And if you're calculating, no, let me withdraw that. Whatever you're calculating, whether it's currents or voltages, you're going to then give the actual values by using the base values. All right? So for every network, you would have already selected the S base for the entire network. You'd have selected V base at a particular point in the network. So having the base values, base voltage and current, base voltage and power, you can calculate the base current at that point, and thereby be able to calculate the actual current, the actual voltage, the actual power where necessary. Are there any questions? Because we finished with the theory now, we're going to jump into the problems now. Do you have any questions?
Not really, sir.
Cool. Alrighty then. So, if we had a network such as this, we'd have to determine the equivalent networks, meaning the equivalent for your generator, equivalent for your transformer, equivalent for your line, for this line, for that transformer. All right? All right? So just to get you started, I'm going to take this question for me. All right. So there's your network. We finish with the network. All right. That's yes.
Yes, sir.
And that's the data. Are we finished with the data? All right, if you're not, you can get it from the recording later. And then here's the question. All right, so given all of this, where do we go from here? We go back to the steps. The first step is that we need to write the, or draw rather, the equivalent circuits. Yeah? I want to replace each component by its symmetrical equivalent and then form the per unit networks, positive, negative, and zero sequence networks. So the first thing you want to examine before you start drawing and getting into this question, you want to examine the data that you're given. All right? And based on the data we have before us, we know that the transformers, yes, and generators are all rated at 100 MVA. What this says to us is that there'll be no need to do any conversion. So we will use MVA base of 100. All right, so that would be our S base. Next, we take a quick look at the transformers. And we see that one is 13.8, 138. One is 138, 13.8. All right. So, and of course, you look at the generators, that's 13.8, 13.8. So what that is saying to us is that there will be no need to convert any of these if we simply select one of these voltages, any one, the 13.8 or the 138, as our base voltage at any one point. All right? So for the transformers and generators, there is no need to convert because we'll need VBS. And we can make VBS 13.8. 13.8 kV. Yes, at the, let's say at G1. Right, so it's 13.8 at G1. We could have also said let the base voltage be equal to 138 on the line. All right? Everybody comfortable with that? Good. For the line, however, because we have made V base 13.8 at G1, it means that the base voltage would be 138 on the line, because if you look at T1, all right, if this is 13.8, all right, that's 13.8. T1 is 13.8 to 138. So it means that 138 would be on the line. All right? Okay. So, as I said, although drawing a network is important, it's good that you just look at your data and make sure that you identify what needs to be converted. It means, therefore, that for your line, you will have to find Z base. Right? So you'll find Z base, and similarly for your load, you'll also need Z base. But note, for the line, Z base will be calculated using 138. Yes, and for your load, it would be calculated by using 13.8. I don't know what keeps happening to my points, but anyway, you get the gist. All right? All right, so now we draw our network. Remember, we are just redrawing the original network, and we are replacing each component by its symmetrical equivalent. All right? So I start by drawing the positive sequence. So for the positive sequence, I start with the two generators. So I have G1 and G2. And of course, I have that because that is how we represent a generator. All right. And that's G1, and then we have G2. So those would be our two generators. Okay? And we, of course, have XG1 and XG2. What were those values? So XG1 was 0.15. And please note that here I did not say X1. I'm giving you the subtransient reactance. And we know that the subtransient reactance is indeed X1. All right? So X1 for generator 1 is 0.15, and for unit 2 is 0.2. So we have 0.15. Please put in the point, right? And here we have 0.2. And of course, that's per unit. And remember that we are just redrawing the original network. And then we have that. Okay? Next, we have our transformer. And because this is the positive sequence, our transformer, we know x1 equal x2. All right? And it's static, so it's just represented by the reactance. So for your transformer, you therefore have that as your reactance. And then, now I can put in the bus bar, but I can simply leave it out because we know that a terminal in a network would represent the bus bar, right? And the terminal is just a point of connection, as we recall from two-port networks. So I can put in that bar, but it really does not do anything for the network, all right? So I can eliminate that. I can ignore it. All right? What we have is xt1, all right? And then I go for the line. Now, the question says that it's in the middle of the line. So what I'm going to do is to draw two reactances to represent the line. All right? So let me just change the color on that. So so this would be one half of the line. This would be the other half. And the fault has occurred in the middle of the line. So it would split the line reactance. All right? And then we come now to the second transformer. All right? So for the second transformer, we have that. And then, of course, we have our load. Now that I'm drawing it, I think I'm just going to put the bus bar, since you're just learning it, you know? Right? And then we have our load. I don't know what's happening today. We have our load. And that is okay. So the values we had, let me just go back for the values. T1 was 10%, T2 was also 10%. So T1 was 0.1, T2 was 0.1. All right. For the line, we now need to find V base. Let's find V base. So V base is 138. Yes, and S base is 100. All right. So Z base.
VB square over S.
Yeah, man. So that would be 138 squared over 100, which will give us 1904. $190.44, all right? So we can find the per unit reactance for the line. It was what? 20. It was 20 ohms. So ZPU for the line would be 20 over 190.4. That gives us 0.10502. We divide it by 2. Right? So we get 0.5251. So this is 0.5. 0.05. All right? So the line is divided. So this is what you'll have for your positive sequence. And the objective would be to simplify this network by looking into the fault point. So you don't want the Thevenin equivalent at that point. Now, whilst it's not difficult, because you're not specializing in power, I'm not going to stress you with it. All right? So what we do is just to say in terms of this module, yes, we will give you the equivalent circuit, and then you must know what to do with it. So for the positive sequence, we know that it would, the network, this network that we have here, would simplify like that. So this would be I1. The equivalent impedance that you calculate, well, in this case, a reactance, that will be Z1. And of course, under fault conditions, we usually take the voltage to be 1 per unit. All right? So we take, that would be 1 per unit. 1 PU. 1 PU. All right? So this is the equivalent network, and that's your positive sequence network. Of course, one of the beautiful things about the positive and the negative sequence, once you have drawn the positive sequence network, you can draw the negative sequence. Right? So positive, take a little time. The negative sequence will be the same network. The only difference is that you will not have any supply.
So
for your negative, for your negative sequence, are you finished with what's on the screen?
No, sir, just a second. Okay, sir.
All right, good. So for your negative sequence, what you'll therefore have, what you'd have, that, for your generators, for your transformer, for the line split in two, for the next transformer, and for your load. Hold on, let me just check. The load was, oh, okay, pure reactance. I just wanted to check. And then, of course, you'll be looking in here. Okay, so you'll be looking in there for the Thevenin equivalent. So it means that your equivalent circuit would be that. All right, so this would be your negative sequence. Yeah. We are on. We have time. All right, now, for the zero sequence, all right, this is where we now have to think carefully about what we're doing. So for the zero sequence, both generators do it. Are we finished with this? All right. So both generators are solidly grounded. So you see that the generators are not earthed through an impedance. So all you have there for the generators, you have X0 being 0.05 and X0 being 0.08. So for the two generators, you'll draw again. These are your two generators. Okay? All right. Now, for T1, you have what? Kind of transformer. What kind of transformer do you have for T1? Nobody drew it?
A step up transformer, sir.
Step up.
That's what I gave you in the data sheet. What did I give you?
Delta grounded.
Huh?
Delta
Delta
transformer.
grounded.
Delta grounded star.
Delta grounded star. So it's 13, the delta is 13.8. Yes? Hello? So on the
Yes.
13.8
Yes, sir.
winding, it's delta. And on the 138, it is grounded star.
Yes, sir.
All right. So, you remember that diagram you drew last week about closing A and opening B, etc.? This is where that becomes applicable. So you now need to look at the transformer. On the delta side, big question, will zero sequence flow? Or can zero sequence flow?
No, sir.
Huh?
No, sir.
No.
No, sir.
So we are going to, oh, come on. We are going to open A and close B.
Sir, you can show why zero sequence won't flow, sir.
You're joking, right? Somebody tell him for me quickly.
There's
We need to
them
move
apart.
on. Tell him fast.
Connected to ground.
Huh?
There's them apart to ground.
There is no part flow to ground, sir.
I didn't get that. Am I? Why is it that zero sequence won't flow?
I'm guessing it's not connected to ground.
Hold on. Then I'm trying to remember if I actually went through it. Didn't we go through a whole half an hour talking about circulating zero sequence in delta, and that delta for delta winding you will not have zero sequence?
Yes, sir.
We went through that last week.
Yes,
Oh,
sir.
yes, sir. I remember now, sir.
Did we not go through that it will not flow either for an ungrounded star?
Yes, sir.
Yes, sir.
Gentlemen, is year 4 the same?
What the flow for a grounded star?
You cannot allow 1 week to pass without reviewing your notes.
You know.
Every single week that I open my mouth, I am building on what I did before.
All right, sir. Thank you, sir.
I'm not getting the answer. Did I?
Figure it out, sir.
You figure it out. I bet you'll never forget it now.
Yes, sir.
All right. So because you have the delta, you have no zero sequence. So we have open A and we have closed B. And then you have the reactance for the transformer. On the other side, for the grounded star side, zero sequence will flow. Yes? So since zero sequence will flow, you close A and open B. What does that look like? We have closed A and B open. We don't have to worry about it. And then we come now to the line. So this is the line. All right. And because, like the transformer, the line is a static device. As a matter of fact, you would also note that in Power Word, the data you supply for your line is similar to the data you supply for your transformer. All right? So you would have to distinguish in Power Word which one of them is line and which is transformer. Both static, therefore represented in this instance the same way. All right? Okay. So this is a line that we have split, and remember the fault was in the middle of the line. So that's a fault point. And we are looking inside here. For the Thevenin equivalent. Now we move from the line to the next transformer. The next transformer, T2, is a grounded star delta. So T1 was delta grounded star. T2 is grounded star delta. All right? So it's just the reverse of T1. So it means, therefore, that we are going to close A. You have your reactance here. And then you close B on the other side and open A. Everybody see that? So this is,
Yes,
and
sir.
then for the load, hold on. Whoa. I overlooked something. It is still correct. It's just that I overlooked a reactance. All right. Nothing that I have done so far will change. So we have the line, the other half of the line. All right. Now for the transformer, T2, look back at the data. What is different for this transformer? What's different for this transformer?
Rate of neutral reactance.
It is grounded to an impedance.
Yeah.
So if it's grounded to an impedance, how am I going to treat it? That earthing impedance. What did we say? What is zero sequence? So this is T1, this is L, or L over 2. On this side, I close A, all right? I then put in the zero sequence for the transformer, but I also put in the 3Zn. I have only turned it because I've run out of space, all right? But normally I'd go straight across. So this would be T20, but this would be 3Zn. And then on the other side, I'm closing B. So I'm closing B because the other side is a delta. You with me? And I'm opening A. So you just go straight across. And then you come to your load. Right, this is your load. And of course, That's it. So this is why the zero sequence creates a bit of a challenge for some students. All right. So let's go through it again. For your zero sequence, these are my generators. So this is G1 0, this is G2 0. This is T1 0. All right. T1 0. This is L over 2, of course, that is the zero sequence. And remember that now with the 60 over the 190. All right, 144. Okay. Of course, divided by 2. Because remember, the fault is in the middle of the line. And then this would be the other half. This would be T2 0. And then this would be 3 times the impedance. So it would be 3 times 0.06. So that would be 0.18, all right? And then this would be for the load. And by the way, Z base for the load, that would be 13.8 squared over the 100, all right? Which gives you 1.9044. Okay? So you would have to go through all of that. And then, of course, then of course, you will have the equivalent circuit. All right, you'll have the equivalent circuit. We're at this terminal, you'll have V0, that is I0. And so V0 in this instance is 0 minus I0 Z0. All right? Are we clear, folks? And so we'll have these networks, and the next step is for us to then look at so that would have been part 1 of the question, yeah? And then part 2 says you should determine the Thevenin equivalent, which we haven't gone through, but it would just be to look in here. And bear in mind that because you have the open circuits here and here created by the delta, the zero sequence equivalent circuit would just involve these reactances. So you'd have two reactances in parallel. That's it. So these would not be a part of the zero sequence. You'll get no zero sequence from the load or from the generators. All right. And then finally, you're given the fault type. It's a phase to ground fault, so of course you know you'd connect the networks in series. But again, just to ensure that we all understand what is happening, take this question for me, please. And while you write, I'm going to ask you to answer to your names.
Sir, will we be continuing the first question?
No. But then again, leave some space and try it for yourself later. It won't hurt. It won't hurt. But this question will cover a lot of what we would have done. All right? All right. Adams,
Present.
Allen, Chavez,
Here, sir. Always is here, sir.
yeah, man. What am I doing? Are you still able to see the question?
Yes, sir.
Yes, sir.
All right, good. All right, let's. All right, Barrett, Shaki,
Here, sir.
Blake, Roger,
Present, sir.
Devon,
Here, sir.
Brown, Gareth, Brown, Bruce,
Here, sir. Here.
Buckley, Burns,
Here, sir.
Campbell,
Here, sir.
Chambers, Daniel, Copley,
Here, sir.
Crosdale,
Present, sir.
Daly,
Here, sir.
Donna, Pleases,
Yeah, here, sir.
Dwyer,
Here, sir.
Ellis,
Here, sir.
Ferguson,
Here, sir.
Finley, all right, let me All right, those are the networks. These are the networks.
Sir,
Yeah.
I never heard my name here, sir.
Yeah, we're not finished yet.
All right, sir. Sorry about that.
Going back to that. All right, so these are the networks. Let's get back to the names now. Francis. Adrian.
Here, sir.
Henry, George. All right. So, Henry, Zavina.
Here, sir.
Hewitt.
Here, sir.
Jeffrey.
Here, sir.
Johnson. Johnson, Antonio. Kamika. Carr.
Here, sir.
Leon. Leon. Lewis, Rajiv. Mason.
Here, sir.
Merchant. Montague.
Here, sir.
Mundell. All right, I think I can remove Miss Mundell from the module. Norton. Phillips.
Here, sir.
Porter. Ramsey. Ready.
Here, sir.
Reed. Christoph.
Present, sir.
Reed. Dario.
Here, sir.
Rose Cullen. Russell. Russell.
Here, sir.
Shand. Shirley. Sinclair.
Here, sir.
Smichael.
Present, sir.
Smichael.
Here, sir.
Smith.
Present, sir.
Thomas Jerome. And Venna.
Yes, sir.
Here,
Present.
sir. Thomas
Was
is here,
that Thomas answering?
Yes, sir.
Answer faster than that. Mr. Thomas.
Yes, sir.
Move
Very nice.
fast enough. All right. Okay, so let's get back to the question. All right. So we have the three networks, and the question asks us to calculate the per unit current flowing into the fault. And by the way, I'll tell you no that this was a question on last year's final exam. All right. So I suppose you would appreciate by now that I don't ease you into anything. I just go for the jugular right up front. So this is a final exam paper question. So I want to find the per unit current flowing into the fault. All right. Now, the first thing you are told is that it's a line to ground fault. All right. So because it's a line to ground fault, we know that networks are connected in series. All right. So the first thing we want to do is just to draw the networks and connect them in series. So we know that we have here our positive sequence. What's happening to my pen? So we have here right, so that's my positive sequence network. This is one per unit. This is one per unit. And this is 0.15. Please, I'm having some issues with the with my pen, so just ensure that you put in the point. All right? And then for the negative sequence, and that is 0.095. So J 0.0975. Okay? And you are told that these are all in per unit, so there's nothing for you to calculate, or to convert. And then for your zero sequence, good. So these are your three networks. You are told that they are in parallel. Okay? You are told, I don't know what is happening to me today. Anyway, we know that the currents for these networks are all flowing out. So if they are connected in series, then we know that and so that's the connection for our three networks. So the question that we were doing before, if we had gone through simplifying those networks and then had defined an equivalent network, since we were asked to do it, since we were told that was a line to ground fault, then we would connect those three networks in this form. All right? And then we want to find I1. Of course, we know that I1, I2, and I0 are all equal. Okay? So it means, therefore, that I1 would be equal to 1 over ZT.
Sir, before you go any further, sir, what type of connection is this you said again? Series?
Yeah, man.
Okay.
For the 0.057. So this was J 0.057. All right. So let's work that out quickly from a place. Okay. All right. So this gives us minus J 3.2841. 284. We had 407. You know, I'm gonna go 2, 3. All right. Remember, this is a point. I don't know what is happening. This thing don't want to do any points. Okay. So that is I1. And of course, you know that I1 is equal to I2 is equal to I3. All right? So from that, what we're asked for, now remember this is occurring at the fault point. All right? So what we're asked for is to find the phase the field currents. Are we finished? So we now go to IA, IB, IC. One. Remember, these are all equal. So of course you'd have I0, I1. Bear in mind, this is where a lot of errors are made in terms of the sequence of them. So we know, as we said before, I1 is equal to I2. Is equal to I0. So we just put that value in and find IA, B, and C. Now, where we need to be careful, if you, let me just go back to what the question asked. All right, so we're asked for the per unit current. All right, so the values that you calculate here, and I'm leaving you to calculate this one. The values you calculate here, these would be the per unit currents because the network that you have is in per unit. So these currents would be the per unit current. Everybody comfortable with that?
Yes, sir.
Any questions?
No, sir.
All right, good. Now, the second part of the question asks for the phase voltages at the fault point. So we have just found the per unit current. Yes. What we now want are the phase voltages. All right. So let's do that. Now, for each network, students, for each network, you are now going to, this would be your positive sequence. Remember, this was 1 per unit. This was 0.15. This is 0.15. And we said that this would be V1. Agreed? It means, therefore, that V1 would be equal to 1 minus I1 Z1. Because remember, I1 is flowing out. That never changes. It's flowing out. And remember, we're dealing with complex numbers, eh? Remember, we're dealing with complex numbers. Of course, the answers that you'll give for A, I, A, B, and C, these must be in polar. But our calculations are all done in complex. So V1 is equal to 1 minus I1 Z1. And that's for the positive sequence. From the positive sequence network, you'll get Z1, V1. So you leave some space. For the negative sequence, of course, I1 here was the minus J3 point whatever we got earlier. All right? For the next network, for your zero sequence, the negative sequence, again, this would be I2, and this would be the Z2, which was 0.0975. Please remember to put in the J. I'm just not able to put that down. I don't know why this is preventing, but anyway. And this would now be your V2. So V2, what's V2 equal to? We dealt with this last week. What's V2?
Sir, minus
0 minus that's it.
ZI2, sir.
Yeah.
Minus ZI2.
Zeros I2 Z2. All right.
Excuse me, sir. I don't think this portion of the meeting is being recorded.
Are you serious? Are you? Oh Lord. Well, I hope you took good notes. Thank you, Mr. Michael. But I hope you all took good notes.
Sir, you can go back to the last slide for 1 second, please, sir. Thank you, sir.
All right. And then for the zero sequence, that would be I0. And then we had here 0.057, I believe. All right. So it will be 0 minus I0, Z0. And that would be your V0. That's V0. Okay? So now that we have V0, V1, and V2, all right, now that we have these, we can find VA, VB, and VC. All right. And that will be equal to T. I don't know why this thing keeps happening. This will be equal to T, V0, 1, V2. And what you will find is that the values you find for V, A, B, and C would correspond to your boundary conditions for a single line to ground fault. All right? Now, the key for this part of the question, and I trust you will know the difference between part 1 and part 2. Part 1 asks for the per unit current flowing into the fault. All right? So you want the per unit current flowing into the fault. Part 2, however, asks for the phase voltages. The answer you would have gotten here, the answer you get here, would represent per unit. So in order to get the actual voltages, which is what you're being asked for, you need to go back to the first part of the question. Not the first part, the opening part of the question, which tells you where is the line? Where is the line located? Where is this line located? Nobody?
Sir, on a transmission network.
Where?
In Jamaica.
In Jamaica. So if it's in Jamaica, yes, what are the two possibilities?
That's
Huh?
13.8. V base equal 13.8.
No, that have nothing to do with base. I'm asking you what will be the voltage on this system. It's a transmission network. What will be the voltage? What are the options? At what voltages do we transmit?
13.8 and
We do not transmit at 13.8.
69.
69.
Or 138.
And?
And
138.
138. Gentlemen and ladies, this is the first thing we did. Nothing I say. Remember, I don't like talking. So if I say something, it must have some purpose. All right? We went through this first week. So now that you have those two possibilities, you now will determine in the exam which of these voltages you are going to use. So you won't come out of the exam and quarrel who right or who wrong. All right? So if you choose 69, then 69 would be the base voltage at that point in the network. So you simply multiply 69 by the VA, B, and C that you get. 69 kV, of course. And those will give you the phase voltages during the fault. Is everyone clear on that? If you decide, you need to state that you're using the 138, if you choose 138, and then find the corresponding actual voltage. Because the answer you would have gotten is in per unit. All right. I know I'm over time. But do you have any questions? Any questions? All right. So what we'll be doing is that you're going to redo this part, this question. Of course, we have gone through the first section, the first two sections. You're going to redo it, okay? And then you're going to also do part C. You'll do part C on your own. You'll redo parts A and B as we have gone through here this afternoon. All right? Yes, you have a lab that needs marking. I need to mark that and return it to you so you can understand how labs are marked. And you'll avoid any error.
Sir.
Yes. Let me finish first. All right, so I'll mark the labs, I'll return them to you. With respect to this assignment, I will schedule it for submission this Friday. All right, so it will need to be submitted by 9 p.m. on Friday. Yes.
Sir, the question says is a line to ground. So the boundary condition for line to ground is IB equal IC equals 0, ain't it? I'm gonna get 0, my calculate, make it 0.001 for IB and IC.
Okay. All right.
0.0012 for IB and IC.
Okay. Are you supposed to get 0? Is that what you're saying?
Boundary condition said IB equal IC equals 0.
But you're getting 0.001. Is that what you're saying?
Yes, sir.
What was the actual value of I1?
I1 minus J 3.284 0.723 amps.
You sure?
No.
That's actually per unit.
Per unit.
Anyway, it was 3.284072249 something, eh? Wasn't it?
Yes, sir.
Eh?
Yes, sir.
Hey, then if you round it off, what you expect?
Yes, so that's slight round off the chew off everything.
I have been warning you about this since you came to me in Network 1. I'm saying to you, when you're doing engineering, especially power engineering, When you carry on rounding off, that is why I mark so hard at this level. When I see people, for example, you would want to put 3.2841. All right? I'm saying to you, because you're dealing with mega and kilo and giga. Once you round off, you must understand that rounding off just, to the 4th dp, you're actually losing hundreds and thousands because you're dealing with power. But to answer the original question, it is not an issue that you have gotten 0.001. Okay? Even outside of the rounding off, what you will find when you're doing especially the labs, is that because you're also supplying a load, you may very well find that there is still current in those other phases. So it will not be zero. I make myself clear. So I'll do the boundary conditions, and I said it at the beginning. I said what the boundary conditions present to you are the ideal conditions. When you're dealing with normal operations, you will still have current in those phases because you're supplying a load, but relative to the faulted phase, they are zero. That said, I have given you the schedule submission time for this assignment. I will leave it there. So, have a good one.
Sir.
Yes.
Quick question, sir. Regarding the lab, sir, I couldn't get used to anything, sir.
Yeah, so I've been told.
Okay, all right, sir.
So I've been told. Oh, what? Well, I gather some persons were cut off from my list. There's Watson. It's Watson here. Nikolai Watson. All right. And Patrick Williams. All right. And Mr. Zhang is here. All right, cool. Okay. That's it. Have a good one.
Same to you, sir.